All right, shall we get started? So a little bit of background. At the Exascale Computing Project, which comes out of the Department of Energy, has an annual meeting. And there are a small number of hundreds of people there. And they have a variety of different BOFs and talks and events and so on. And Mike Haru has kind of shifted his position in the last year. One of the things that he's doing at the DOE is to sort of take a forward look at different kinds of projects that the DOE has and what it is that they're trying to do with them, and vet them to make sure that we're working on the right ones. Try to encourage others to join and look for new things, but also to look for, there's an increasing emphasis on collaboration among the different teams that have various different goals. And to that end, when I pitched this to him, he said, yes, I love this idea. Let's cover this. So we did a BOF. He actually submitted it, called Toward Common and Interoperable Software Infrastructures. So what I'd like to do today is just point at that and look at what it is that we covered. And my key takeaway was, there are lots of folks that have some common interest in some common infrastructure. And they have different flavors and interests and so on, but it's indicative, the fact that we got 17 groups from within the DOE to kind of say, yes, I'm interested, and at least in theory, I'd like to participate in this. There seems to be a fair bit of interest. The place where there's the rub, of course, is a sort of, how do you actually make this happen? There's, of course, a natural tension between if you're a project that's already very well underway, then making much modification is, hey, it's kind of late. I've already baked and I've already moved on. And if you're a new project, you're so desperate to be able to get something going so that you can meet your next milestone and not get killed off as a project, that you don't have time to do a lot of software architecture. But people's, I think, general assessment was that there may be some common infrastructure that we want to go look at here. And so I'll give you some highlights of this. Many of these challenges are common themes that we've been talking about along with HiHat of, we just don't have enough people to be able to do things right and to be able to get things really well tuned up. There's another thing that I think is an emerging issue, which is that what we're seeing more and more with HPC applications is that HPC really more and more refers to scaling out and scaling up and using the kinds of software disciplines that we have exercised throughout the community in new ways, but that we may be pulling things in that are more than just the traditional modeling and simulation of scientific computing, and that we're now going into HPC plus X, where that could be visualization, could be deep learning, could be machine learning, could be data science, could be other things, and that those things together make a mashup of a new flavor of application and that are spanning these multiple application domains. And as that happens, then these issues of interoperability and so on across these different packages that are being brought together make are more of an issue. And so there's a question about, hey, do we want to collaborate, and what would that collaboration look like? So I'll highlight some of the trends that we've noticed and that I kind of heard other people talk about here. As you have these mashups across these multiple domains, there's a question of, do you want, you could just sort of, the traditional way is dump all the data out to disk and then completely parse it in again from scratch. But you could do better if you have a common data model between the two, and you can, even if they're in different processes, if they're on sort of a platform with a thicker node where you can have multiple processes and a lot going on, and lots of memory to share, that you may want to have more memory management, common memory management with this. And if you have these thicker, highly connected nodes, you may want to tailor, sometimes I do need to move my data across the network and sometimes I don't. And I may want to figure out where do I best want to put it to observe NUMA and other kind to optimize for NUMA. As things increase in scale and become more unpredictable, then of course you're in the realm that most of us care about, which is being able to do asynchronous things rather than doing everything bulk sync and having some more dynamic scheduling. If there's more heterogeneity in the computer memory, there's more concern for NUMA. And people are excited about being able to, the huge speedups they can get from lower precisions, use of deep learning, iterative solvers, whether that's in tensor cores or something else, then that leads to more of a careful management of precision and quantifying the error and uncertainty. And this is one that I was somewhat skeptical about, but people that know much more about this than I do say, yes, there can be different kinds of building blocks and analyses that you may want to do for these. So you'll see this theme of there's a number of primitives at the bottom. Yeah, I'm sorry, let me make this bigger. Oh, I'm not. Am I sharing? I hope so.
Yeah, you're sharing.
You're sharing, but you've got a pretty small window open. There you go.
Yeah.
That's better.
I'm sorry.
That's better.
Take care of that. Sorry about that. You have these different primitives, and we may be able to identify some different services that could be relevant across multiple application domains that are built on top of this. And some of the new kinds of things that we see, we spent and visited some guys at the Livermore Labs, Katie Lewis, Jim Baze, and others, and a number of the, among the things that they're doing are, when they have so much data, they're saying, hey, let's extract features using 2D visualization type techniques and use that to be able to and so that's yet another thing that could be added as a feature, if you will, on top of this, or some sort of a service that could do this. And with all these new technologies and increasing heterogeneity, people are just trying to keep pace and trying to tune and validate these things. And it's easy for them, at least in theory, to nod their heads and say, yes, if I had some of these primitives and services that we could agree on, maybe it's Apache Arrow to start with, maybe it's some other things that might help me actually to keep pace and be able to have a well-tuned platform for whatever it is that I have. And so this, then leads to, do we want to take a layering approach with this? And what are the kinds of things that we want to do with this? And you may end up with building blocks layered on top of primitives like Raja on top of OpenMP tasks, on top of CUDA Graphs is something that is a thing that's under investigation. MPI on top of UCX or OFI is another. So we, is George here? Let's see, George Paselka here, right? So George had also sort of framed, some of these other technical challenges and questions that we may want to have with this. So we essentially got all of these folks to give, I've never seen this done before, where we actually had 17 lightning talks in a row and kept the time. It was amazing. It was incredible. I think it was a small miracle. So these are all different areas. If you just want to stare at this for a while and look at some offline, I'm not going to go through them all, of different folks that said, yes, for these, I have various different kinds of challenges and opportunities. This is reminiscent of what we did back as we kicked off the HiHat effort back at GTC several years ago. And so I'll skip through these, get to the end. And if there's anything that people want to stop and talk about here, you're welcome to. But we had a variety of different items that were covered. Getting to the end. Thank you for those of you that are here that contributed to and presented there too. Thank you. And here we go at the end. So we had did kind of a survey looking across the different domains of interest as to how interested people were in these. So scientific computation was not surprisingly pretty high there, but we had a reasonably broad interest in other areas as well. And I think this is a shift from what the answers would have been even just 5 years ago, in terms of the level of interest in some of these alternate domains and looking at the mashups. We looked at primitives, and essentially all of these rated quite high as things that people may want to look at and investigate. And then services of interest. And again, these varied. Precision and uncertainty was less of an interest in some of the instrumentation and the 2D feature extraction, but there are still some folks that were interested in those. So given this, this to me is yet another data point that yes, people seem to be interested in this area and looking for opportunities for collaboration. So I think that what we've looked at, for example, the Legion folks have some proposals for a data model that they're working on, and one of the things that's of increasing interest is Apache Arrow for data management. There's some overlap here. Adios has also done some work in this area, and this is it's a set of people that we're looking to do some collaborations with to essentially look at in those places where there are a number of people that are already using some infrastructure, and so they don't have to use something completely different, and we can, underneath them, come in and offer a better implementation in that underlying infrastructure, and still be able to keep it interoperable. Those look like some of the more promising opportunities. So I can go back up with this and highlight again the list of projects. Over here. Does anybody want to speak to or comment on or have questions about any of these in particular? All right. Any other observations or whatever about this, of what looks promising to you, and what do you take? What are your takeaways from the highlights of what we've just presented? I'll wait with some silence here to let people speak up. Some of you were here for this, so Antonino and others were there and presented. Do you have any other comments or feedback from that? People are kind of quiet. Y'all are out there, right?
We're still here.
Just us crickets.
Okay. So I think the my take with this, and sort of where we are with the HiHat stuff is in general, is that I think that the place that we really want to focus on is where we can get traction with what it is that people are want in solving specific problems. And so the graphs area is one that's, I think, gotten most traction. And we presented last month some layering of OpenACC and OpenMP on top of graphs. This is something that's continuing and moving forward. And we also have talked in the past about executors and layering those on top of graphs. and that looks reasonably promising. Jared presented that, and if you didn't see it, his examples have been open sourced up on GitHub, so you can go have a look at that. I don't know what the download or whatever statistics have been for that to see how many people have actually gone looking. I haven't followed up on that. But those are a couple areas that I think that we're pursuing with this, and the next two areas that I mentioned that I see us being able to go after most are in the area of Apache Arrow, underneath which you could extend that with the data model and with some data movement primitives, and also the Adios effort for I/O. So those are a couple different areas. Anybody else have any other key nominations for aspects of infrastructure that are of greatest interest? All right. Well, let's let that rest there, and I'll pass the baton on to you, Stephen.
Okay, let me just share a thing here. This.
CJ, you have to let it go so he can pick it up.
Okay. Can pause share? Nope, that's not it. Stop share. There you go.
Okay, let me try this again. Okay, can you guys see something?
We can. The CUDA 10.1 task graphs.
Perfect. Yeah, so this CUDA's task graphs is it's the lowest level execution system which fits inside all of this layering. And so when I've talked about this with people recently, it's clear that people want a good picture of how this fits into the picture of layering. I want to stress that CUDA Graphs itself just works within CUDA, right? So the stuff that you launch to the GPU, the stuff that CUDA can manage, is doable in a task graph. But this is just one component of the whole hierarchy of graph work that describes the whole workflow of a program. And so I want to keep that in context, because really all I've got to talk about right now is sort of, here's the thing that we've built. We've built the first steps of it. There's more steps that are coming. I can report out on the performance of it, which is actually pretty interesting, so I'm going to do that today. But there's still a lot of other areas where you want to make sure it fits into your whole hierarchical execution context. And maybe we can sort of mention that at different places, or ask a few questions. So I'm going to tell you what we've got right now. Some of this will be familiar to most of you, so I'm going to sort of skip rapidly through it, but just to refresh your memory about very specifically what it is that CUDA has today. And this is in CUDA's 10.1 release that came out in February. So you can go to the web, you can download it, you can run this. All of the numbers which I show are numbers which I got from just the basic downloaded web thing on my own desktop computer, not writing super crazy fancy code, just writing sort of regular CUDA code. So anyone should be able to reproduce these results very simply. So as a quick reminder, CUDA itself already defines a mechanism for describing a graph, a directed acyclic graph. CUDA has work queues, which we call streams, and you can put work into these streams, which is implicitly in order. The implicit part is key here, because if I put A, B, and C into the same stream, then they intrinsically will get a dependency between A and B and C. I can put weight tokens between streams, something we call events, and that allows me to branch and fork and join. And effectively, a series of 3 streams on the left here can be mapped, or exactly describes this graph of dependencies on the right. So what we've done with CUDA's graphs is we've taken a programming model that is already sort of dependency based, and we've allowed you to describe it explicitly instead of just implicitly, and do a few other things with it. So the key insight that we had for where this could make a significant difference in terms of performance, and there are functional differences that you can get as well in terms of simplicity and programming model. But in terms of performance, we recognize that creating work on any device, but in particular this sort of asynchronous stream-like work on the GPU device, because you're creating asynchronous work that runs separately on a different processor on different threads, is that there's really three parts to any work creation. And so with graphs, we've split those things into explicitly three parts. You've got the definition phase, where I say, if you remember on the previous slide, here are my streams A, B, C, D, E, X, Y, all of the connections between them. And you have to define that in a very strict way. In CUDA streams on a graph, we allow you just to sort of throw the nodes there and hook up the dependency arrows between them, and you get a graph that you're building. It's mutable, it's playable with. Then the second phase of work creation is to actually build the execution structures that the hardware needs. This is analogous to an operating system needing to create process tables, create a new virtual memory space, all of those types of things. The instantiation of the work, it involves allocation, initialization, setup, configuration, all of the things you might imagine. And then finally, you have the execution phase, where I say, okay, all of these work descriptors which I've created, kick them off and start them running now. And by splitting things into those three stages, we recognize that there are different optimizations available at each stage, and that not every stage needs to be done all at the same time. So every single time that I run the work. In particular, the basic goal of a graph is to define it once and run it many times. So phase 1 and phase 2, which may be more expensive than just simply kicking off work, the cost of those can be amortized by repeatedly executing the work. And this is obviously something which I think is familiar to everybody. And just a quick recap of what operations a CUDA's task graph can do is anything that CUDA can do. So today in CUDA, I can launch kernels which run on the GPU with many threads. I can actually insert in my dependency chain a callback to a CPU function, so I can invoke incorrect dependency order CPU code, and a graph can do that as well. Any one of these nodes could be a CPU function call, which could internally call MPI send or whatever you wanted it to do. There are limitations on what a CPU node can do, and I'll get into that if people are interested, but it's not particularly relevant to this specific conversation. You can do asynchronous copies with DMA engines, memory clears, and of course things even inside CUDA, the graphs are hierarchical. I can create if you imagine an application that wants to do some LAPACK operation, a triangular solve of a matrix, and it will then invoke under the covers some BLAS operations. I can have a hierarchy of graphs with my main application, my LAPACK operations, and then BLAS operations deep inside them. And, graphs are intrinsically hierarchical. It would be bizarre not to have subgraphs as possible nodes. So, since I'm going to tell you about the performance that I've seen, because that's really the most interesting thing, I think, since we've heard the programming model before, I'm just going to break down for you where time is spent running code on the GPU today. So it's a fully asynchronous processor. It's a separate processor that lives across the PCI bus. But the first thing that happens when you kick off some work is you've got this blue launch operation that you have to get through, which involves literally building those structures that I showed you earlier, the section 2, if you like, the instantiation piece, and sending some transactions across the PCI bus to activate the GPU. That takes a certain amount of time, 2.2-ish microseconds. Then there it's going to be an initialization phase actually on the GPU, where the hardware creates the threads, sets up the execution context, brings things in from memory, loads up the caches, does all of those types of things. And that grid initialization phase itself takes another 1.5 or something microseconds. And then finally you're going to get to running your kernel. In this case I'm showing for short kernels, because what we're talking about here with CUDA's graphs implementation, we're saving you individual microseconds. So if your kernel is running for tens of milliseconds, then this is going to be noise. With the exception of the launch, I'll get into that in a moment. But in general, if you've got short workloads, if you're strong scaling where you have very small parcels of work and your kernels are short, you can end up in this particular example with numbers which I've measured about a 50% overhead spent both getting the work started and in between kernels when you're running the work. So the first thing that we do, and there's two places that this sort of three-step breakdown helps. The first is to reduce the CPU launch side reduction. If you remember, the idea was you define it once, run it many times. The run many, therefore, the goal is to have the launch be less expensive, and truly this is what happens. I'll show you some numbers coming up. And that's great. That reduces some fraction of the overhead. Obviously, that's a single operation cost. It's, the more you launch, the more time it will take, and therefore the more the reduction is. But something which occurs every single kernel is a sort of almost a better target for optimization. In my particular example here, completely by accident, it worked out to be approximately equal savings. But I can also reduce the grid initialization time. When I can see my dependencies, I can prefetch those caches, I can pre-initialize those things, and so I can get the hardware running a little bit faster. And so you're saving, in this particular example of very short running kernels, a couple of microseconds, that's about long enough to do about a 32 cubed FFT or something very relatively small. Maybe you could invert a 64 square matrix. Those types of things you can do in 2 microseconds, and then you'll be looking at a saving of a quarter of the time. So in general, the speed ups that I've measured, and this is just on my own personal box, I appreciate that I've seen it go faster and slower on different boxes. Mine's with a Volta Quadro board and a 3.5 gigahertz Skylake. Is that the relaunch time is pretty steadily about 7 to 8 times faster than the stream launch. This is not of course, accounting for the time it takes to set up and create the graph. I'm literally just looking at the reuse of the graph here. Likewise, that dark green section on the previous slide that I showed you, I'll just go back and point it out, the grid initialization region here. That is this graph on the right, where we've reduced those overheads by about 40% by doing things like prefetching into caches and so on. So your per kernel overhead is shorter, and your launch time is shorter. Remember, this is just reduction in overheads. I'm not making your kernels run any faster. I'm not saving you any flops. I'm not boosting the clock rates. There's none of that. I'm literally just taking away some of the time that the system spends creating and initializing and executing things. So in actual number terms, here is the best case that I was able to measure on my own machine. And so this is with a large graph. I think this is looking at 100 or 200 nodes in a graph. I have some actual plots later for you. It's pretty steadily on about 2.1 microseconds per launch on my machine when I am launching individual kernels. So, launch kernel A, B, C, D, E, F, G, and it's going to take you about 2.1 microseconds per launch. If I'm relaunching this on a graph, then you're looking at about a bit under 1/3 of a microsecond, 0.29 in this case. And the standard deviations here are pretty small. So to put into context, excuse me, a 100 node graph on my machine will take me about 210 microseconds to launch in a stream, and it will take me about 28 microseconds to launch that from a graph. So, it's an approximate order of magnitude, which is pretty nice. Likewise, in execution time, the gap between kernels to do all of this prefetching and stuff has gone down from about 1.5 microseconds to about 1.1 microseconds of time. And again, measured on my particular card in my particular machine. But this 40% is something that we see pretty reasonably across a large number of systems. And there are exceptions that some systems do much better. Here is an example, because I wanted to show not just a synthetic benchmark from my machine, but something that some of our engineers had actually run. And in this case, these are people who are working with embedded systems, and because of the ARM processor, launch is more expensive because there's additional cache invalidates that have to be done because of the memory model of ARM, and so the speed up is in fact greater when I'm launching, greater than my 7 to 8x. And so these are real numbers from real inference networks for automotive applications in this case, where you can see that and in the blue lines, it's a very straightforward get something running on my machine. The orange line is where I'm sort of, if my work is very small, I can run many instances of this at the same time, and in fact your performance improvements get better when you're running many copies of these at the same time, because of course there's more opportunity for keeping the machine busy and that sort of thing. But we're seeing, reasonably consistently either break-even performance or improvements in performance for relatively little effort. And I'll show you exactly what I mean by relatively little effort. But so these are very encouraging numbers. I think to actually get these numbers was less than a day of work for our engineers. It was the amount of code that had to be added was about 20 to 30 lines of code to the existing application, which is pretty encouraging to be able to get very, very good speed ups. So a reminder of exactly how you get that code, or maybe not so much of a reminder as a description of it. We give you two ways. The first and simplest way of turning your CUDA work into graphs. If you remember, I said that normal CUDA launchers already form a graph. We've created this mechanism called stream capture, which I literally press record when I'm launching work, and instead of the work launching, the work itself does not actually launch. It is instead just used to build a graph on the fly. In this case, I might launch kernel X and then make a call into a library. The system will recurse into that call and embed whatever work the library call creates into my graph, and then maybe the library call returns to me, and I will follow up with a node Z in my graph, and then I end up with this X, A, B, C, D, and Z graph that you can see on the right-hand side. And so literally by saying begin capture at the start and end capture at the end, if your work is already asynchronous internally, and that's a big if, I'll get to that a little bit more in a moment, then we literally just turn the stream into the graph that it already is and give you back a handle so that you can relaunch it many times. And this is exactly why those previous graphs were sort of from about 20 or 30 additional lines of code. It was literally a matter of annotating the code in these ways.
People often ask the question here about what the semantic effect and timing effects are for during the capture phase. You want to comment on that?
I will get to the timing effects a little bit later. The semantic effects are important, which is that you must have replayable work. So if, for example, my node X here is an initialization operation which zeroes out all of my memory buffers, when I capture that into a graph, then every time I run my graph, I'm going to reinitialize all of my memory buffers and I'll be sad. So you have to be aware that what you are looking to capture is the stuff that you want to run repeatedly. You can't just blindly go and put a capture at the very beginning of your program and end capture at the very end of your program and just go, because not all things are replayable. The other thing which is extremely important is that these are asynchronous task graphs, which means the work that you capture must be wholly asynchronous. That means two things. One is that if my library call here, the thing that is in my picture doing ABCD, if my library call is launching some work and then waiting for it to give back a result, consuming that result, and then launching more work as a result, if I've got a dependency inside that library call, that is not capturable because that is an immediate requirement. It's not replayable. Remember, I mentioned when we capture the graph, we're not actually running the work. We're just pressing record. And so when I capture the graph, that nothing in your code is allowed to assume it's already running. It means that if my library call were to do some MPI communication, the data that I might be MPI sending is not going to be ready yet because I haven't actually run the graph. I have to put my MPI send receive into its own graph node to do that communication in the right dependency order. So it's not just a dumb begin capture, end capture. This is probably pretty obvious to the people on this call because we think about task graphs a lot, but it's been an education point I have found to make people are not even aware sometimes that they are doing synchronous or dependent operations inside their programs, and then you try and turn it into a graph, and boom, it's actually not asynchronous, and they run into that problem. They've got to do some rearrangement. So which
is different than some other systems' notion of tracing and then, oh, I've seen this trace before the last time I actually ran it, and so I'll replay a trace of what I actually ran before. This is not that.
Yes, exactly. It's not a trace. It's not capturing a memory image or anything like that. It is just capturing the work that you are creating. So sort of the two golden rules are no initialization or one-off code in your graph, which is usually pretty simple. And the harder one is no implicit or internal dependencies with your work creation code. You can't synchronize to bring back results while you're creating the graph. And very importantly, you can't concurrently expect your graph to be running alongside a thread on CPU, for example. Remember, this is heterogeneous work. You can't have them both running side by side unless that execution is also described in the graph, because you're not allowed to make assumptions that the work is running, and you can't make assumptions about the work being, or the work is by definition the same on every single, each time. The final thing that is important, and I think I may have a slide on it later. In fact, do I? Well, if I get to it, I'll re-highlight it. The final thing that's important is when I'm capturing your work, I'm capturing not only the work you're trying to kick off, but all the parameters that you're giving to it. Because I'm going to go ahead and pre-initialize all of the work structures. That includes your parameters to your kernels. It includes the arguments to your callbacks. It includes the size of your memory copies. This is an exact recording of what you are doing. And that has also proven to be a sticky point. We're working on that. I'll give you one slide at the end, which will describe a little bit about what we're looking at. But the graph is an exact replay of a single instance of a recording, which means that if I pass any pointers to X and to Z or into my library, those pointers must be the same on every invocation. And for the automotive guys I was talking about before, they have cameras coming in on their self-driving cars, and they triple buffer their cameras. What they actually do is they create 3 different graphs, one pointing at each buffer, so that they can invoke the correct graph for the correct buffer because the pointers are baked into the graph. And that is where we're getting a lot of this performance from, but the price you pay is that you have to make sure that your program is arranged so that your pointers remain the same pointers. And as I said, at the very end, I'll give you a hint towards where we're going to relax that restriction, but that will of course come with overheads. As well as creating a graph from a stream, you can create a graph natively, directly, and immediately by saying create nodes, create dependencies, then go ahead and instantiate it. The code on the right is a little bit of pseudocode, to indicate this. But many applications find it more convenient or more natural to be able to create the nodes of the graph directly instead of sort of mapping your workflow onto streams only to turn it back into a graph again. I think I've seen a few people gravitate naturally towards this. As we add features into graphs that maybe streams cannot do, then this will become a very important way of creating work. Note that this direct creation composes perfectly well with stream creation. You can blend graphs created in 2 different ways. Remember that any node of a graph can be a subgraph. You kind of created that subgraph any way you like. These things are completely composable. It's just a matter of what is most natural to your program. And so, a description of a code description of how these things might look, the code transformations that need to happen. Stream launch on the left here, I've got a basic for loop doing n iterations of A, B, C, D, E all the way through to Z, and then I'm synchronizing, waiting for my results. That would be a very typical kind of CUDA program on the left. The important thing that I want to point out here is that I've got data index I here. So my data on the left is changing with each iteration of I. My pointer is changing. That was something I just said you cannot change in a graph. So on the right-hand side, what you see here is I begin the capture of the same sequence, A, B, C, D, E, all the way through to Z. And I begin that outside of my loop. This is part of my initialization phase of my program now, not my execution phase. But I have to pass it just a single data pointer here. I cannot pass it a different data pointer on each iteration, otherwise I'd have to recreate the graph. As I say, more on that later. But the basic model is I capture my graph, instantiate it, and I get this graph that I then iterate n times and just simply do the launch. It is this code pattern on the right that I was showing you with the factor 7 to 8 speed up. The difference in per iteration of this loop of the loop on the right versus the loop on the left. And so sort of the code is, if your code happens to be simple and asynchronous already, it is literally just a matter of a few lines of code to make this happen, but obviously mileage does vary. So a quick summary of what you can't do with graphs, and I've mentioned this to you before, but it's always worth calling out again. Graphs is literally just like any execution. It does what you tell it to do. If you say run node A on GPU 0, node A will run on GPU 0. Run node B on GPU 0, node B will run on GPU 0. While I can span multiple GPUs with a graph, because CUDA can do that automatically itself, I'm not going to pick where to run these things, because this thing on the left, A and B on the same GPU, is equally valid to the thing on the right, A and C being on the same GPU. The graph does not describe to me which one is better, but locality between, like cache locality, memory locality may be important to you. I leave it to you to tell me which GPU to run which graph node on. I am not going to make that determination for you, because I just cannot know. I am the lowest level executor. I don't know anything about your application. There's also no data dependencies. The dependencies follow CUDA's model of execution dependencies. That is to say, you can say B runs when A finishes. B does not run when A's output is ready. You can build that yourself very easily if you want. I'm going to let you do so. But I am going to continue to run execution dependencies, because that is the way that the GPU runs work. And honestly, these lines at the bottom, all data dependencies are trivially mappable to execution, but not vice versa. So I built the lowest level thing that was the most versatile. And the other thing, which probably is obvious, is no structural changes to a graph. I'm not going to take graph nodes of work that you create and magically recognize that I can combine them into a single operation. I certainly don't. If I don't have enough intelligence to be able to place your execution on a particular locale, I certainly don't have enough intelligence to be able to fuse your operations. While the earlier description, let's go back to this piece here, the automatic placement, that is something that HiHat as a whole should be able to lead towards and give guidance on, seeing more of the information. And these data dependencies themselves can help define where locality is, also as part of HiHat as a whole. I think that the splitting and merging of nodes requires compiler-level information about the code that is being run, and is a much more challenging problem, I think, outside the scope of task graphs itself. I would willingly be happy to have a debate about that, but I feel very strongly that that's the case. And what you can do is, of course, you can reissue work very rapidly. We've seen this. You can have, and I'll just reiterate this, heterogeneous node types. I can have CPU work dependent on GPU work, DMA copy engine work dependent on CPU work. You just define the nodes in the sequence that you want, and CUDA will make sure that the right thing is notified at the right time. And then cross-device dependencies are legal, although, as I said, I'm not going to pick which device you run on. It's entirely up to you to run. Oops, and I realize this is basically an amalgam of the previous two slides, so never mind. Ignore that. And let's get to the performance. I've got a few minutes more. So to give you a quick description, one of the interesting things that comes out of this as the graph launches, I'm moving towards order 1 launch, but it's not still order 1. That the amount of time it takes to launch work is not independent of the amount of work that I am launching, even when I have defined a graph. And there are a number of reasons for that, and I'm happy to answer questions on it, but I want to get to this point first. When you have only a very few nodes in your graph, then in fact, at the asymptotic limit down the bottom left-hand corner here, when I have a single node in my graph, it is exactly the same performance to launch a graph of one node as it is to launch a single kernel into a stream, because I'm creating exactly the same amount of network. I think it's maybe 4% faster. It's not particularly interesting. That's almost a good litmus test, because if you're doing the minimum imaginable work, it should take the minimum imaginable time, and the whole thing effectively is dominated by the PCI transaction that is necessary to invoke the GPU. So as I move away from sort of one node in my graph to, say, 10-ish nodes, then I start to get sort of a more constant and steady performance, because I'm starting to the time to launch the work starts to become large compared to the individual PCI transaction time. And so what you see is that while it asymptotically reaches 7-ish X performance speed up. On the right-hand side, I've got the graph running out to between 100 and 1,000 nodes. I had to draw them in two graphs, otherwise this stuff on the left gets squished into a very tiny space. And so what you see is that the transition into being highly efficient is in that 10 to 15 graph node area. That is to say, if I'm launching A, B, C, D, E through to J, that's 10. That would be 10 kernels. Then my speed up starts to become very interesting, and it pretty much ends up more or less constant around a 7x faster execution than a stream.
Do you want to comment on why it falls off?
I actually have no idea why it falls off at the moment. I have not yet done that much investigation. It does actually pick up a bit later. It oscillates. In fact, if I run this out to a 10,000 node, it actually oscillates. And I'm completely unsure why that might be. So if you remember my earlier drawing, this is a plot of that blue launch stuff at the very beginning. If you remember, I had a let me zip back to it for a quick moment. I showed you this thing here. This plot here, that first plot was the blue launch, and now I will show you the plot of grid initialization, where I also mentioned it was going 40% faster, and that's a pretty steady sort of 40%. It's a little bit better in the early numbers, but again, as I get past about 15 to 20 nodes, then I'm pretty steadily about 40% less overhead when running with a graph, and this comes from these cache prefetches and other things that I can do when I can see the whole dependency tree. When I know what's coming next, I can warm up the chip ready to run it. And so that's that dark green section of it. So we've got the blue section on here, which is a steady-ish 7x speed up when you've got a decent amount of work in your graph, and we've got a 40% improvement in the dark green. That's a per kernel overhead improvement. So if your kernels are very short running, then you care a lot more about this than if they're long running. And in terms of just plots to see what things look like, I just generated a bunch of plots. Stream launch is pretty nice and steady. The more nodes I launch, the more microseconds I launch. It's a very linear thing. Graph launch is also very linear. As I said, at the moment, it's not an order 1 operation, and that's because of various buffering and things that we have to do. I'm still working on that. It will take a little bit of time, but I hope to get there. But you can immediately see, of course, the gradient of graph launch 7 times shallower than the gradient of stream launch, which is not a surprise, but very much that same linear function. So I did something interesting here. And CJ had asked about timings of creating graphs. I actually said, okay, what's it look like if I actually factor in the time to create the graph as well? I'd previously been advertising it's going to take about twice as long to build the graph as it takes to build the stream, but it turns out I was wrong. It turns out we did better than we expected, and that in fact, graph create and launch is itself faster than just stream launch. And that's pretty interesting to me. That means that if you remember, let me jump back to my piece of code before, which I showed you here. If you remember, I had these data index I operations in my stream, which I could not capture in a graph. My graph has to reuse the data each time. Then if instead I end up in a situation where I must rebuild my graph for some reason, maybe I can do 10 iterations or some new pointer changes, or even if for some reason I need to do it every single time, the interesting thing that this graph here is showing me is that I actually can still do better than just a raw stream launch. That the performance benefits of launching a graph are sufficiently great that they do cover the cost of building it. I'm going to zoom in one more finally on the small graph, because if you remember, there was that curve of performance gain on the small graph end. And you can actually see here that where the overlap happens, this orange line is the graph create and launch. And you can see that if you're creating the graph from scratch and you've only got one node in your graph, it is definitely a lot more expensive to do that. But my crossing over point here is a sort of 10, 11 graph node region. If once, and the simple fact from this previous graph here says that once I am past that 10-ish kernels, there's 10 nodes in my graph, I am always 100% of the time faster using a graph than using a stream. And that's an interesting story. That says that you can actually do better than break even in pretty naive code, and if you end up needing to change or update or modify your graphs, you can still end up in, it's not fantastically different. I think here's the final, the sort of the final graph determination of that, the final chart, which shows that in terms of purely launching, this blue line crosses over about the 1 point at 10 nodes, and then is always 18-ish% faster than doing it through a stream. And the orange line factors in those cache prefetches, that execution 40% overhead optimization. And so if you factor in the end-to-end runtime of your graph, you actually see that you cross the 1 point at about 6 nodes in my graph. And so my graphs, so if I'm ever at a point where I'm launching 6 or more kernels, you might as well just slap a graph around it. This is for build it, compile it, run it, and delete it every single iteration, and you still save yourself 20% of time. It's kind of an interesting result. So yeah, those final plots which I had before, low number of graph nodes on the left, high number of graph nodes on the right. As you start off, as you build up towards 10 to 15 nodes, your speed up improves. But even here on the bottom is my orange line, which is saying I'm still at 20% better on every single time. That's what the sort of the big picture looks like. And so I think I'm going to stop there. I've got a couple of code samples and other things in case it comes up in conversation. We've got about 5 more minutes. Took a little bit longer than I expected. But if anyone has any questions, I'm happy to answer them.
Can you go back to slide 23, I think? What are the restrictions what can be placed in CPU calls?
Okay, let me see. What are the restrictions that can be placed in? Okay, so at the moment, the restrictions are exactly the same as a CUDA stream, because we literally cut and pasted the code. But those restrictions will be relaxable in the future. So today, a CPU node cannot issue new CUDA work. And the reason is that inside the driver, we're holding some locks that are not recursive locks. And therefore, if you go around creating new work, then you deadlock. So while we're working around those locks, this rule will apply. But once I have a graph, I can work around these locks because I can see inside the whole dependency chain when I need to hold the lock and when I need to release the lock. So I don't have to be as aggressive as I am with stream launches. So in the future, graph work will allow the CPU node to perform any other operation, creating and building a new graph and launching it if you wish, if that's what you want to do. But today, the existing stream constraints exist because we have not yet specialized the locks around graphs. So I apologize that it's not there yet. Right now, your CPU work is not allowed to interact with the CUDA runtime inside your CPU code. You can certainly use MPI or do whatever else you want, but you're not allowed to go around launching new work. The CPU callback thread has to exit to release the locks, and so you may deadlock.
Okay, thanks.
I'm wondering also about CPU work. How CPU work scheduled? Which thread executes it, and how does the CUDA runtime and driver behave with respect to locality thread pinning, especially in cases where owning cache might be important? For instance, if outside the graph some threads create work and populate caches, and then one wants to consume it within the graph. And
so I think there might be two things worth commenting on in there. The first is that today, when CUDA runs a CPU node in a graph or even CPU callback in a stream, it uses its own internal driver thread to do that. I'm certainly interested in discussing better ways to do this because obviously a lot of runtimes like OpenMP or something manage their own threads, and it would be much more useful to be able to target one of the user's threads. But today, you get a thread inside CUDA's driver, and so you have to set up your own condition variable to hand off control to a thread of your choosing on a core of your choosing and a runtime of your choosing. So at the moment, the CPU callbacks are pretty naive, and it's up to the programmer to hand that control off. In terms of getting data sort of generated by your CPU work handed back to the GPU, the limitation that I cannot issue memory copies is a very severe one, which is why we're actively working on reducing it. It means that if I generate work, or maybe I do an MPI receive, and I wish to hand that received data back to the GPU to run with, I cannot issue a DMA copy to make that happen. That means today my options are limited. Tomorrow, when we've managed to resolve the locking problem, that will be simple. But today the options are limited, and either you have to use a GPU direct mechanism of having the MPI stack drop the memory directly into the GPU, or you have to leave the GPU in PCI map system memory that the GPU can read. I'm afraid that it's definitely awkward at the moment, I acknowledge, but please bear with me. This is only version 1.
So follow up to that, are CUDA graphs compatible with the GPU direct or DMA?
It depends how you define compatible, in as much as, I mean, the graph will not break it. The work that you issue in a stream around GPU direct RDMA will also be issuable as a graph. I think the biggest constraint there is that the pointers are locked into the graph, and that might be an issue for some RDMA implementations. But the general rule is if you can do it in a CUDA stream, you can do it in a CUDA graph.
Okay, I think I might have used the wrong nomenclature. What I was referring to is the CUDA API, which includes stream weight value and stream write and stream weight value. So yes, that could be a mechanism to coordinate concurrency between a graph and existing CPU work, and this is what I have been I have been planning to explore and try, but I have the opportunity to ask whether it's worth trying. Then I would rather.
I think at the moment we're not supporting stream weight value. I don't think there's any strong reason why not. We might have thrown it in as an experimental thing that we're not advertising. I actually don't remember. It was a little while ago we did the stream capture. It's definitely on the list to support if we're not already doing it sort of just as an experimental freebie. By all means, give it a try and see. The stream capture will fail immediately if it doesn't recognize the command, because there's no functional reason why we would not support it.
Okay, thanks. And third, very quick follow-up is: do you plan to support execute on record?
No, not at the moment. And the reason is that if the capture fails while the record being captured, if the capture fails, then I end up with partially executed work that I have no way to unwind, and so I think it doesn't make sense.
Okay, well, I'm not sure if you did get this feedback before, but when it comes to a larger legacy application, this creates a challenge that one has to completely rewrite the entire computational schedule specifically for CUDA Graphs. So before being able to even use it, because there is no other way to have the workload recorded and executed in case of if CUDA Graphs don't exist because the backend is different.
Right. So I've run into that before, and one code pattern here which I've been able to use is to build the graph on my first iteration, so it's sort of embedded directly in my code. And so I literally have an if statement. If the graph doesn't exist, then the execution runs. If the graph does exist, I skip the execution creation and I go straight to the launch. And this sort of inlining is the way the automotive guys got their tests to run. They just drop them inside their main execution loops. And that proved to be reasonably easy to do. And so then I can have an if streams versus graphs at the top, and that if then would become, it would be sort of if not graphs or my executable graph is null, then go ahead and immediately do the work, and then go ahead and build it.
You can keep going. I'm afraid I have to drop off to run another meeting here. So.
Yeah, we actually have
Thanks very
Yeah,
much.
I'm afraid I do as well.
to.
Yeah.
Well, thanks everyone. That's a good meeting. I'll post the video shortly.
All right. Thanks very much.
Everyone. Cheers.